Let's look at question number 6 of our homework assignment number 2, part B. Yeah. Here, so when we work on specific input, here we are given input with order like this, right? But this order will be used when we count the number of comparisons. When we merge subarrays, at that time we will use this given initial order. All right? Yeah. So in this case, we need to run the standard merge sort. All right? Yeah. So not the best case, not the worst case. Just this particular case. Okay? All right. Let me show you. But when I show you, I want to use a different example. Yeah. I want to leave this question to you. So I cannot just solve this question directly. Right? So I will change. Yeah. So I use my example to show you the detailed steps. Yeah. So then, after you understand this example, so you can work on this question. So in my example, I changed this 9 to 7. Okay, yeah, 7 elements. Right. Yeah. So let me write my example. My example. All right. Yeah. X1. Yeah. Here I just choose some random order. Yeah. Random order. Yeah. Right. Like X4 less than X3 less than X7 less than X1 less than X6 less than X2, one more, right? X5. Yeah. Suppose this is the given input in this particular order. Now, let's run the standard merge sort and see how many comparisons do we need. All right. First, yeah, because these 7 elements, when we arrange, remember, yeah, so this is the order information. Yeah, so this information is the, order information. Yeah. But the array given, array still X in this natural order, right? X1, X2, X3, X7. Yeah. So our processing order, we need to use the natural order for our processing. So this order information, when we make our decision, we will use this order information. Okay, all right? Yeah. So in this array, we have 7 elements. X1, X2, X3, these 7 elements. 5, okay, all right? Yeah. Divide and conquer. Yeah. Split in the middle. Yeah. So the first divide is here. Yeah. So we get these 2 subarrays. The first divide. Okay. All right. Second round. Yeah. These 3 elements at the right hand side, the second round, yeah. Second round. Okay? All right. Yeah. Then third round. Right? Yeah. Third round. All right. Yeah. So that's the divide all the way down to the case that we cannot divide anymore. Yeah. Then we do the merge. So when we do the merge, now we need to use the given order information. Okay, all right. First, we merge two adjacent subarrays, two adjacent subarrays, two adjacent subarrays. Okay, yeah. So the first round, merge. When we merge these two, yeah, we apply the standard merge operation. We compare x1 and x2, but after we compare x1 and x2, we need to use the given order here. Okay, x1 here, x2 here, so x1 less than x2, so the comparison result we put here, x1, x2, comparison result, all right? Yeah, but, and one comparison, okay? All right. Here, x3, x4, we look at the order information here, x4 less than x3. So we write x4, x3, yeah, all right. Then this is also one comparison, okay? All right. Here, x5, x6, x6 less than x5, right? So we should write x6, x5, and also one comparison. So this round, the subtotal, 3 comparisons. Yeah. This round. Then next round, merge these two adjacent arrays. Then these two adjacent arrays. But when we merge, yeah, we use the standard merge step. Compare x1, x4, right? Yeah, because standard x1, x4 as our first comparison. So x4 is smaller. So that as a result, x4 is the first element. Next one, x1 and x3, right? Yeah, x1, x3, and x3, second one, all right? Then, yeah, because the right subarray all in place, all the elements in the right subarray are in place. Then all the remaining elements we just put in place directly, right? Yeah. So this case we need 2 comparison, right? Because one put the x4 in place, another one put x3 in. Then the remaining no comparison, right? Yeah. So in this way, yeah. So we only need 2 comparisons, right? Then here, this place. Compare x6 and x7. x7, look at x7 smallest, right? Yeah. So in place. But then we can put x6, x5 in place directly without comparison, right? So one comparison. So this round, 2 plus 1, right? 2 plus 1 equals 3 comparison. Yeah. All right. Then the last round, merge these 2 subarrays. All right. x4, x7. x4, x7. Look at the order information. x4 in place. Then x3, x7. Look at the order information. x3 in place. All right. x1, x7, look at the, order information, x7 in place, right? Yeah. x1 and x6, yeah, x1 in place, right? Yeah. All right. Then x2 and x6, so x6 in place, right? Yeah. Then x2 and x5, x2 in place, then x5. Okay, see? So when we put all these elements in place, yeah, except the last one, so we need 6 comparisons, right? Yeah, 6 comparisons. Yeah. Yeah. The last one we don't need comparison. Okay? Yeah. So you can see, merge the last two subarrays, we need to use the worst case. Yeah, so that's the worst case. All right. So the last round, six comparisons. Then total, adding up, total. Okay. 3, yeah, so 12 comparisons. Okay? So that's the way you solve this problem. Okay? For question number 6, so you use this way to solve it. Okay? Yeah? All right. Yeah, but other than this question, I may like to talk about another question, yeah, because the previous two, one best case, one worst case, yeah, because there is some special convenient notation I may like to, recommend it to you. Best here, worst, yeah, best or worst, the working process pretty much the same. Yeah, pretty much the same. Yeah. Only difference is at formula. So I only need to show you one example. Yeah. All right. So here, let me just do the best case. But when I do best case, I don't want to solve the original question, right? Yeah, I leave the original question to you. So let me change this 10 to 8. 8 elements in our example, okay? Yeah. All right. Yeah. So let me work on this 8 element. Yeah. But this time, best case. Yeah. So this time is different from the previous one because we just apply the formula directly. Yeah. So we do not do the specific comparisons. Yeah. We just write the formula directly. Yeah. All right. So let's draw an array with 8 elements. x1, x2, x3, 4, 5, 6, x8. All right. Divide. So the first divide, this place, 1. Okay. All right. Second, 2. 2. Then 3. Then 3. 3. 3. All right, so then merge. Okay, all right. Merge these two adjacent subarray. All right. So here, because in question like this, for every merge, so let me write some basic information. For every merge, after we apply the formula, best case, worst case formula, after we apply the formula, so one is best case, the other is worst case. Okay, all right. We need to keep useful information. So what information do we need to write down? Yeah. So So key the information we need. Yeah. So two items we need to keep the information. Okay, all right. The first one, number of comparisons, right? Yeah. Number of comparisons. The second piece, the array size. After the merge. So the second part is also useful. Yeah, definitely the number comparison, we need to accumulate the number comparisons from all the mergers. Yeah, so definitely we need that. But this second piece item, the array size after the merge, we also need to write down. Because this one, when we apply the merge in the next round, we need to use this information. Okay? Yeah, so based on that, so when we write our merge result, so I want to use a simple notation like this. Okay, all right. Yeah, so here, merge 1, 1, m is 1, n is, sorry, yeah, so the best case formula we know, yeah, here we know, minimum of m and n. All right, so we apply this formula. Minimum of these two numbers, this 1, 1, so minimum is 1. So the number of comparison is 1, all right? Then I use a vertical bar to separate the second piece of information, the array size after the merge. What's the array size? 1 plus 1. Yeah. So we also need to store the array size number. Yeah. So we separate in this way. All right? So this one merge these two subarrays. Yeah. Result, 1 comparison, array size 2. Okay? All right. 1 comparison, array size 2. Yeah. 1 comparison, array size 2. All right? Yeah. Now, the number of comparisons. Okay? Yeah. Here. Number of comparisons. All right, yeah. 4, right? 4 comparisons. So that's this round. Yeah. Then, next round, merge. But this one, when we work, we need to work on the size, right? 2, 2, okay? 2, 2. The minimum of 2 and 2, also 2. Array size is 4, right? So we write this way. Okay, here we work on 2 and 2. So now you know why we need to write these 2 items. Yeah. So the merge result 2 and the array size 4. But when we count the number of comparisons, we use the comparison parts. 2 plus 2 equals 4. Okay, all right. Now, then when we do the last round merge, we need to work on array sizes, 2 array sizes. So minimum of 4 and 4, that's 4, right? Comparison. And the size, 8. Yeah. But the number of comparison is 4. Okay, all right. So now we add these 3 numbers, we get 12 comparisons. Yeah. All right. So for this question, so I recommend, yeah, so when you work, you need to arrange your information in a friendly way. Yeah, because otherwise you get a mess. Okay? Yeah. So a lot of information you couldn't find. Yeah. Yeah. So here we try to organize our data, yeah, intermediate data, in a well-organized way, so we can find them easily. Yeah. All right. So that's the, the hint I feel, when you do the work, yeah, it could be helpful. All right. Yeah. So for other questions, yeah, I just leave it to you. Yeah. So now I want to move to other topics. Yeah. All right. Let me move to the part B first. Yeah. Remaining time. Yeah. Part B. Yeah. All right. All right. Introduction to hashing. Yeah, so let's learn this technique, a special technique. All right. So this is a search. Yeah. So this technique belongs to the search type questions. All right. Why using hashing? Yeah. So first, let me give you the, the background information. Yeah. So why people want to use this technology for hashing? Yeah. So let me compare the current search algorithms we have learned at this point. Search algorithm. Yeah. We just learned two search algorithms, right? Yeah. The first one, linear search. The second one, binary search. Right. Linear search, unordered array. Binary search, unordered array. Yeah. Efficiency, linear search, big O of n. Binary search, big O of log base 2 of n. Okay? All right. Yeah. And these two search algorithms, we need to use comparisons, right? Comparison operation. All right. Yeah. Yeah. So now, today, we will learn the third one, hashing. Hashing. Yeah. Hashing, quite different. Yeah. First, yeah, when we apply this technique, unordered array. So we do not require it is ordered, like, binary search, unordered. Yeah. Yeah. Right? Yeah. Second, yeah. So about the efficiency, yeah. Big O of 1. How fast is it? How can you do that? But this is the average case. Average case. Okay? But also good. Average case, you can get a big O of 1. also really good. Okay, all right. How can you get that fast efficiency? Yeah, so that's why this technique is very interesting. So we want to learn. The idea is very smart. Okay, all right. Yeah. And then another thing is, if we compare these three search algorithms, so there is some important difference. Okay, all right. Yeah. So we all do comparisons here. Yeah. We need to do comparisons. Yeah. But when we do comparisons, our the objective is different here. Yeah. All right. For the first two, 1 and 2, when we do comparison, we do comparison for order info, right? Yeah. Because out of comparison, we get order information. So what order? So we have equal, we have less than, we have greater than info, right? Yeah. After comparison, we can get the order info. So that's the first two search algorithm. But for hashing, the third one, not for order info. Yeah. So we don't care the order info. Okay? So for what? For matching. If you get a match, okay? If you get a match, so what's that? You compare if it equals or not equal, okay? Yeah. So if it's not equal, then unequal, so no match. Unequal, no match. So equal, so you get a match. Okay? Yeah. Yeah. If you get a match, that's what we need. We want to see if we have a match or not. If no match, then we do something different. If it matches, then we find it, right? Yeah, search, we find it. If after our comparison, no match, yeah, so then we need to do another operation, another search operation, until we find it. Yeah, so, but we never use the order information. We never need to know which element, which key is larger, which key is smaller. We never need to know that. Yeah, so that's the different focus. Yeah. All right. Yeah. Next, let's look at how to find a data item with a given key. Yeah. Given a collection of data dynamically. Yeah. So data items keep coming in. Yeah. Dynamic data. So we need to add it every time when we get a new data item. We need to add it to our data structure. Yeah. So here we still need to build a data structure. Okay. Yeah. Yeah. So in order to support this fast search algorithm, we need to design an advanced data structure. Yeah. All right. Yeah. So there, because each data item, how to locate it, right? Yeah. So each data, in order to locate one data item, it must have a unique key. Search key. Key. Yeah. Each data item must have a unique key to be used to identify this data item. Yeah. All right. Then, so now we need to consider, so what is the fastest way to find a data item in the collection, the given current collection, matching the search key, because the search key must be given. So which one in the current collection can match the search key? So that's the question. All right. Now, so let's look at the data structure, design part. Because we have freedom. So here, no restriction on the data item, right? On the data structure. So we can use our imagination to choose a special data structure. All right. Handle dynamic data efficiently. So what do we mean handle insertion and deletion, right? When you insert a new data item, your insertion operation should be very fast. When you delete a data item, then that operation also very fast. Okay, all right, Here, let's do comparisons. Linear search, binary search, and there is another special search algorithm. I didn't talk about it, because this one has some special properties. A big advantage and a big disadvantage. The advantage is so big, so nobody uses it. So that's why, people rarely mention it. But here, for inspiration, we want to put it here. Because this one, although in a real world situation, it is useless. So this index search in a real world situation, it is useless. But it has some very nice property that can inspire us to design our hashing search algorithm. Right? All right. Data structure, we use array, right? Here, we all use array. All right. Performance or efficiency, so big of n, big of log n, log of n. And index search, I will talk about this. What's that? Very simple. Bigger of 1, very fast. All right. Ordering, so unsorted, linear search, sorted, unsorted. All right. Then dynamic data, linear search, dynamic data, So you can add it to the current array. But binary search, when you insert a dynamic data into a currently ordered, that operation is very expensive. All right. So this, because you do not need to maintain the order. The reason the binary search insertion is costly, because you need to recover the order. For the other two cases, you do not need to recover the order, right? Because they are applied on unordered data. So that's why, for the dynamic data, very cheap. All right. Efficient sorting, because at a certain point, people may like to sort the data. Then linear search, no efficient sorting. The binary search, it's ordered, so there is efficient sorting. Okay? For other cases, in order to do the sorting, then that operation is very expensive. Okay? All right. Now we want to consider the new algorithm. New algorithm, we want to, Yeah, because we like the efficiency of the index search. Yeah. So here, let me say something about this index search. From the name. Yeah. Yeah. So actually, in our textbook, there is another name for this index search. Direct addressing. All right. Direct addressing. Address. Yeah. Yeah. Index search, think about in an array. Yeah. So in an array, if we use the array indexes as the search keys, so for this one, yeah, why we call it index search? Yeah. So use the array indices as the keys directly. Yeah, so that's why another name called it direct addressing. Okay. Yeah. Because array that's the address information, right? Yeah. So another name for it, direct addressing. Okay. Yeah, same thing. Yeah. Then it is very fast. Yeah. Because when you have a key, yeah, key that's the index. When you have an index, you can find the element directly, right? That's why we call it direct addressing. Okay. So you use the key when a key is given. Because you use the key, the same thing as the index. So you can go to that specific location in the array to find the element. That is extremely fast. Okay? So that's why, yeah, so it has the big O of 1 efficiency. Super fast. Okay? Yeah. Yeah. So that is its an advantage, big advantage. Right. So in our new search algorithm, so we like to have this property. We like to have this property. Yeah. But this algorithm is useless. Yeah. So you will see. Yeah, the reason is it wastes too much storage resource. It wastes too much storage resource. Yeah, waste. Yeah, yeah. So I will use some examples to show you the point. Yeah. So that in the real world situations, nobody wants to use this algorithm. Yeah. Too wasteful. Okay. All right. Yeah. So our new search algorithm, we want to eliminate that drawback, big drawback. Yeah. Wasting too much storage resource. Okay? Yeah. Yeah. So if we can find a smart way to eliminate that big drawback, then we get a very efficient search algorithm. Yeah. So that's the idea. All right? Yeah. So for other things, yeah. Yeah. So let me go to the next. Yeah. So here. Yeah. Next, I want to generalize idea of the index search. Yeah. But I need to point out the big drawback. So why it is useless. Yeah. All right. Direct addressing. Okay, yeah, all right. Key property, yeah, so here, key and index of array. So one-to-one correspondence. Okay, yeah, direct. Main problem when the keys are long, yeah. Sometimes you may have long keys, right? Yeah. When the keys are long, but you only have a small number of elements, yeah, that could happen. Right? Yeah. In that situation, waste a lot of space. Yeah. That's its biggest drawback. Okay, all right. Yeah. So let me use a simple example to show you this point. Yeah. How to use space efficiently. Long keys. Yeah. For example, social security number or student number, usually relatively long keys, right? Yeah, yeah. 7, 8, 9 digits. Yeah, all right. Many digits. But think about, in one class, we have one class with 40 students. Yeah, so it's a pretty large class, right? 40 students. But comparing with 9 digits, the ID number, right? So let's call it ID numbers. Yeah. So 9 digits ID number. Then, if you use the student ID numbers as the search keys for these 40 students, yeah. If you use the index search or direct addressing method, yeah, you can see how much space do you need to use? Yeah, yeah. So if you use directly, because each index of the array is this 9-digit number, you may need to use, about 1 billion locations, right? So you need an array in order to use this 9-digit index. So you may need to create an array with a size 1 billion. But you only store 40 students in that 1 billion size array. So that, you waste too much. 99.9% more than that space wasted. Yeah. So that's definitely, that's the reason I said it is useless. Yeah, so nobody wants to do it in this way. Yeah, no matter how fast it is. Yeah, nobody wants to do it in this way. Okay, all right. So the next we want to fix this problem. Okay, huge space resource wasting problem. We want to fix it. Okay, all right. How to make keys shorter? Yeah, the way to fix it, we want to make the keys, long keys, shorter. Okay? If we can find a reasonable, easier, simple way to make a long keys to shorter keys, yeah, then we can use this method, right? Shorter, yeah. So then the question, how to map keys to slots? Yeah, because we need to use, slots to store the student information. Okay, so each student we need to have one location in our data structure, one slot in our data structure to store the student information. Yeah, all right. So we need to map long keys to slot numbers. You see, long key map. Yeah, so this word is important. Yeah. This word tells us how to solve this problem. Mapping. We need to find a smart or simple and also nice. Yeah. So mapping function. Yeah. So mapping strategy. Yeah. So let's look at the mapping question. What is a good mapping? Yeah. Now you can see the main point of the search algorithm. We need to work on the mapping strategy. Okay? Yeah. Good mapping, fast calculation. When you do the mapping, you plug in some function, right? Yeah, you do the calculation, evaluate some special function. So the calculation should be very fast. Yeah. All right. Another property, evenly distributed among all the slots. Well, after mapping, you get a shorter keys, right? Yeah. So those shorter keys correspond to slot numbers. Yeah. Then you when you have a good mapping function, so you want those shorter keys corresponding to the slot numbers are distributed relatively evenly. Yeah, so relatively, we can only say that. Yeah. Not absolutely evenly, right? Relatively evenly, yeah, among all the slots. Yeah. Then, another property for a good mapping strategy, not sensitive to any pattern. Yeah? Because sometimes the keys, the search keys may have some special pattern. Yeah. But your mapping strategy should be robust enough to overcome those special patterns. Yeah. Yeah. So that's the considerations when you design a new mapping function. All right. Yeah. So let's use this idea, use this guidelines here to design the new mapping functions. All right. Yeah. 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 So we call it hash functions. Yeah. So this technology, yeah. The data structure we use to store our data, so we call it hash tables. Yeah, hash tables. Yeah. Hash functions. Yeah. So the search algorithm, so hashing. Yeah. All right. Yeah. B12 hash functions. Yeah. So here we look at two simple hash functions. Yeah. First one, division method. Yeah. The second one, multiplication method. All right. Division method, hash function. Yeah. 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 So that's simple. Yeah. Division. We do division. Assume that all keys are natural numbers. Sometimes keys could be strings, right? Yeah. String values. Yeah. Yeah. But string values we can convert to digits easily, right? So if we like, yeah. So, yeah. Or we can treat it as numbers. Yeah. All right. So here, let's just use the numbers here. Yeah. All right. There are m slots. Yeah. So m slots. Yeah. How to map a relatively large key k to one of the m slots? Yeah. That question. Yeah. Here we use the division algorithm. H function, hash function, h of k equals k mod m. Yeah. Yeah. That's division method, yeah, because you do integer division, but you only keep the remainder. K mod m, you only keep the remainder. The quotient, you throw away. Okay. So you do not look at the quotient number. So you just take the remainder number as your slot number. Yeah. See? Yeah. Easy to calculate. Yeah. Okay. This method, very easy to calculate. Okay. All right. Evenly distributed. Yeah. So in this aspect, its performance may not be very good. Yeah. Yeah. May not be robust. Yeah. Because for some special patterns, it does not perform well. Yeah. All right. Caught by any pattern. Yeah. So many patterns you can break this mapping method easily. Yeah. So you make it work very slow. Yeah. For some special patterns. Yeah. All right. So let's look at some example. Yeah. All right. The division method with m slots. Yeah. Example 1. Yeah. Let's consider m equals 15. Yeah. 15. Yeah. So this number. when we use this direct modular operation like this mod 15, then when you have a pattern, look at the pattern, the key is a multiple of 3. Suppose the given keys, so you have a sequence of given keys. All those keys are multiples of 3, that pattern. That pattern will make this mapping function not efficient. Yeah, all right. Because h of k, yeah, based on this modular operation, it's also multiple of 3, right? Because 15 is a multiple of 3. K is multiple of 3. After you do mod 15, the remainder also multiple of 3, right? The remainder also multiple of 3, right? Yeah. So here, yeah. H of k, the remainder, minus original number k, so that is a multiple of 15. Multiple of 15, yeah. K is a multiple of 3, then 15n minus a multiple of 3 number k, yeah, that h of k number is also multiple of 3. Okay? Yeah? Yeah. So if it's a multiple of 3, then in the 3, think about, in this 15 slots, the usable slots only 1/3, right? Yeah. So here, let me draw a little bit, okay? Draw some of the slot numbers here, okay? Slot number 0, 1, 2, 3, 4, 5, 6. All right? Yeah. Yeah, because the slot number after the mapping, the hk, this function, multiple of 3, then this slot can be used because the multiple of 3. This slot can be used. This slot can be used. But 1 can never be used, right? Slot 2 can never be used. Slot 4. You can see the usable slots only 1/3 of the total space, total storage space. Then you waste 2/3 of the space, right? In this way, you waste 2/3 of the space. Yeah, multiple 5, but not multiple 3, right? Yeah, not multiple 3. Yeah. So here we assume k is a multiple of 3. Yeah. If we assume k multiple of 5, then 5 can be used. Yeah. All right. Yeah. See, so we want to have a robust function to break this pattern. Okay, so this pattern easily breaks our hash function. All right. So the division method with m slots. Now another example. 2, m equals power of 2. Yeah. If power of 2, when you do the modular operation, basically, because if you use the binary number to view it, you truncate the bits, right? Yeah. So if 2 keys have the same last R bits, yeah, because you only truncate the last R bits, use the last R bits as the slot numbers. So if 2 keys have the same last R bits, then they are mapped to the same slots, right? Yeah. So by this hash function, they are mapped to the same slot. Yeah. Same slot, we call it collision. Yeah. So it could happen. Same slot. So there is a collision. When a collision happens, then you need to resolve the problem, right? You need to do more work. Yeah. If you have large number of collisions, then the efficiency of this algorithm will be very slow, yeah, because you need to do too much work. Yeah. So that means this method not robust. Okay? Not robust. Okay? A good choice of division algorithm. Okay? A good choice is a prime number, yeah? Because prime number there is no factor, right? Like 15 is not prime number. The reason, yeah, that 15 is a bad one because it's a composite number. All right? So in order to avoid the problem like the 15, so we want to choose a prime number that is not too close to power of 2. Yeah? If it's close to power of 2, then you have a lot of collision problem. Okay? So in order to make it, better, stronger, yeah, so we want to choose the M, yeah, with that property. Yeah. It is better to be robust again, yeah, just relatively better. Yeah, relatively better. Okay? Yeah. So this method, yeah. So we can. It is empirical. Yeah. People need to do experiments. Yeah. Yeah. All right. Yeah. Yeah. It's very hard to prove. Yeah. But it is possible to create a special pattern to make it perform poorly, because people can design some, very special pattern to, yeah. Even that, yeah, because the question is, even that special pattern exists, yeah, the probability is very small, right? Yeah. If the probability is very small, that means the method is still acceptable. No. 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 All right. So that is the division method. Yeah. Yeah. Another one, improvement. Yeah. So we're not very satisfied with this one. Although simple, yeah, but it looks not very strong. Okay. So another one, yeah, we want to make it better. That's the multiplication method. No. This time, yeah, so we can make it much stronger than the division method. Oh, question? Yeah. So I saw Lauren asked me question. Is M or N number of? Oh, okay. Yeah. All right. Yeah. Yeah. M or N number of data points. N. Yeah. Right. Oh, good question, Lauren. Let me explain it this way. So Lauren asks, M or N. Yeah. Yeah. Do we have N here? So actually here we do not have N. We have key, right? We have key, okay? Then we have certain number of data points. Yeah. So here the question, I want to ask this way. So, yeah. Actually, M is not data point. M is different from the number of data points. But related, okay? M is related to data points. The meaning of M, the number of slots, right? Number of slots in our hash table data structure. And we know we should have sufficiently many number of slots to hold the number of data points, right? So this number of slots should be greater or equal to n, yeah, so here, yeah, n, let's define n, number of data points, okay? That's the relationship, yeah, so let's assume n is number of data points. Yeah. So the slot number, yeah, because we need to have many slots, right? Yeah. So m greater or equal to n. So usually greater than n. Yeah. Although so this equal is the extremal case. Equal is the extremal case, right? Yeah. But too tight. So this equal case is too tight. Too tight means, no flexibility. Yeah. Too tight. Yeah. So usually people want to leave some room. Okay. So m greater than n, and leave some room. Okay. Yeah. So suppose this is a hash table with m slots. Okay. All right. M slots. After you store n data points, yeah, n data points only occupy part of it. Okay, let's say 90%. Okay, 90% of the slots occupied. 90% of the slots occupied by the data points. Yeah, like that. So you leave some room for flexibility. Okay, yeah. If it's too tight, then your collision problem is very big. Too many collisions you need to handle. Okay? So efficiency will be slow, relatively slow. But if the ratio, m over n, the ratio is too big, then you will waste a lot of storage space, right? Yeah, you will waste a lot of, so you want to, find some balance point between, okay? You do not want to waste too much space, but you do not want to have a lot of collision problem. Yeah. So, all right, so that's the point. Yeah. All right. Yeah. Yeah. So multiplication. Yeah. Let me give you the formula of the multiplication method first. Yeah. So then, more discussion I can leave to next time. Choose a constant capital A in the range between 0 and 1. Yeah. So this capital A number, important. Yeah. So what is that? Yeah. So that constant A, we do this mapping. So our function. So we make K times A mod 1. Yeah, because you remove all the integer part. You keep the fractional part. Yeah. Then m times that fractional number after you throw away the integer part. Yeah. So only the fractional part remains. So you do multiplication. Multiplication, it could be a non-integer. You take a floor function to convert it to integer. Yeah. So that's, you use that number, yeah, as your hash key, h of k. So good selection of capital A can break most patterns. Yeah. So, yeah, because you can select A should be an irrational number. Yeah. Yeah. A, so golden ratio, for example, golden ratio, this one, yeah, but you throw away this one, yeah, because you only keep the part between 0 and 1. Okay? Yeah. So then, yeah, because this number there is no patterns, right? Yeah, no specific patterns. So you want to use this, pretty much random digits, right? Yeah, close to the random digit. This random property to break all the patterns. Yeah. Okay, yeah. Pi is another. Okay, pi, but you need to throw away the 3 integer part. Yeah, pi, another. Yeah. So basically all the irrational numbers are good candidates for this multiplication method. Yeah. Rational numbers. Okay? All right? Yeah. 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 And you can imagine this method should be, much better than a division method. Yeah? Yeah. Yeah. And, so this multiplication method, very simple to calculate. Yeah. All right. Yeah. All right. Yeah. So that's let me stop right here. Yeah. Remaining part, I do not want to go too far. Yeah. So I just give you some basic introduction, concept, ideas. Yeah. Yeah. So this part will appear in our part A. Okay. Yeah. Part A. Yeah. Part A of final concept questions. Yeah. So we cover this part. Yeah. Yeah. All right. Yeah. So that's it. Next week we still have 2 classes. So basically I will do reviews next week, 2 classes. Yeah. First I complete the remaining. Yeah. So part A I have 1 slide. Part B I just have 1 or 2 slides left. Yeah. So if I finish those remaining part, then I will do review for final. Okay? Yeah. Next week, 2 classes we will do review.